Thank you very much for the kind introduction. And as you know that I am working in the Department of Metallurgical Engineering and Material Science at IIT Bombay for past 11 years. After my superannuation from Bhabha Atomic Research Center in 2014. And though my basic degree was in solid state physics and electronics, that was almost 50 years back that I have taken that degree. After that, I have worked in various fields of material science, plasma processing of materials, and it's all interdisciplinary. So physics has, as of today, it has no connection with my basic degree. But anyway, whatever I have done in the areas of plasma processing of materials and how this plasma processing or plasma technology can be used for various manufacturing process, that is the theme of my presentation today. Now, before I start, it is my humble duty to acknowledge the support of all my colleagues or co-workers from Laser and Plasma Technology Division, Bhabha Atomic Research Center, Department of Metallurgical Engineering and Material Science at IIT Mumbai, Institute of Advanced Studies in Science and Technology at Guwahati, my collaborators from India and abroad, and a large number of students, both PhD students and MTech students, who contributed to various activities. Now, basically, these plasmas, I do not know how many of you have even heard the word plasma. Can you raise the hand? How many of you have heard something about plasma or something? I think none, or maybe some few. So, but I will introduce this subject to you starting from the almost scratch, and then we will go to the advancements in this particular area. Now, this I will come back to this slide little later. First, let me tell you what is this plasma. Okay. See, plasma is an assembly of positively free and negatively charged particles and neutrals. See, you have, let us say, gas, any gas, hydrogen, nitrogen, oxygen, whatever it is. When you remove one electron from one atom, you end up in getting one ion and one electron. Okay? And when we talk of atmospheric pressure, we talk of 10 raised to 19 particles per cubic centimeter. Very large number of particles are there surrounding us. And continuously there is a cosmic activity or background radioactivity, those events are going on. So because these cosmic rays and background radioactivity radiations, they are high energetic radiations. So they basically strip off electrons from the atoms, so resulting in one ion and one electron. And of course, see, this is a dynamic process where large number of electron ion pair formation is going on. Simultaneously, there are going to be recombinations, and this is a continuous process. So now, when this kind of so basically we call this removal of the electron from the atom as a ionization event that we have studied. Most of you have studied in your 12th standard. What is ionization? Ionization is basically removal of the last outermost electrons from the orbit of the atom. Now, in this process, like when you generate these electron ion pairs, very large in number, see, one ionization events gives you one electron and one ion. So number of electrons and number of ions, that is Ne is equal to Ni. Ne is the number density of electrons and Ni is the number density of ions, and they must be equal. Okay, they are equal. Then see, we are again not talking about few electrons. Like when you talk of degree of ionization, see, as I have told you, in one atmosphere we have 10 raised to 19 particles in 1 cubic centimeter. So when we talk of ionization even in the low pressure, like at a pressure which is reduced than that of the atmosphere, we talk of number of electrons per centimeter cube as 10 raised to 12, 10 raised to 13, 10 raised to 10 minimum of that order. So very large number of electrons and similar number of ions. So, and again, when the ionization takes place in the medium, it is not that everything is ionized. Very small fraction of the atoms, they are ionized, and large fraction is still unionized. So now what you have got? You have got electrons, you have got ions, and you have got neutrals. And all these particles, they are colliding with each other. They are colliding with each other. When they are colliding, they are transferring their momentum from one particle to the other. There may be some recombination, there is an energy exchange, and from here again two body collision problems that you have studied in your 12th standard might be knowing that when the particles of identical masses, they collide with each other, they exchange their momentum completely. But when electron, which is a very, I just take example of hydrogen atom. Hydrogen atom, see, it has one proton and one electron, okay? And electron mass is 1800 times more than that of the proton mass. So ion is going to be 1800 times higher mass than that of the electron. Now when this light electron, it is having some energy, but when it collides with the heavy ion of hydrogen or ion of hydrogen, it transfers very small fraction of the energy, and that is evident from the two body kinetics, like collision kinetics. So, and at the same time, when there is a continuous input of the energy, now from where this input is coming. Now I will come to what is plasma. See, it is, if you see the popular books, you will see that plasma is defined as the fourth state of matter. What is the first state? Solid. You put energy into solid, it will become liquid. If you put more energy into that, it will become gas. When you put more energy into that, the gas will be ionized. Simple is like you take ice, water molecule. It is at low temperature, it is solid. You heat it, it becomes water. After that, it becomes steam, and you go on dumping energy into that. It will go into hydrogen, oxygen, hydrogen ion, electrons, and all sorts of things. So this state of electron, ions, and neutrals is nothing but your plasma state that is defined here. Okay. Now this plasma state has to have certain. See again. Now we are talking of, as I told you. We are talking of in 1 cubic centimeter degree of, even though the degree of ionization may be less than 1%, almost 10 raised to 8 to 10 raised to 10 electrons, similar number of ions and remaining neutrals. So all these particles, now they behave collectively. Electrons are lighter mass particles, ions are heavier particles. So electron cloud and ion cloud, they oscillate with respect to each other. So they have certain frequency called omega p, that is plasma frequency, which should be very, very greater than the collision frequency of the particles among themselves. Number of electrons should be decidedly should be equal to number of ions. And then if in this assembly of electron, ions and neutrals, if you put any perturbation, like some foreign charge or something, that you need to do in the processing. Actually, when I discuss the examples with you, that time you realize that. When you put some perturbation, so basically perturbation means in terms of potential, like putting some electrode onto which you put some voltage or something. So if it is negatively biased, it will repel the electrons, it will attract the ions, and that basically if you put the positive potential, it will be surrounded by the electron cloud, and the effect of this positive potential will not be felt onto the remaining plasma particles. So basically that length of the plasma medium should be very, very greater than that the perturbation, that is lambda d. I think this is not working. The lambda d, which is the perturbation length, then plasma frequency, that is the electron cloud that are oscillating with respect to the ion cloud, that should be very, very greater than collision frequency. And if you take a sphere of radius lambda d, the number of particles in that sphere should be very, very greater than 1. That is number of electrons basically for that shielding to be effective. And again, it shows the collective behavior. That means if in this room we have the plasma, something happens in that corner, the effect will be felt there. Because see, all these, now you are talking about charged particle state, where you have electrons, ions, excited neutrals. Excited, why they have become excited? Because of energy transfer from one particle to other particle. And in this process now, see, the charged particles, they are moving, so they generate the electrical currents. When there is an electrical current, that is associated with the magnetic field. So basically, you are ending up with the electromagnetic field into that whole plasma volume. So these particles, now they move under the influence of this electromagnetic force or electromagnetic fields, and they behave in a collective manner. That is evident from the, like, these parameters I defined as plasma frequency and all these things. Now I will come to the okay. Now this basically, these plasmas, The simplest example that is available that I can give it to you is the plasma that is generated into your electrical tube light. Because you have the two electrodes under the reduced pressure, there is a gas, you put the electrical energy, and because the gas is under the reduced pressure, because the ionization that is created by the background radioactivity or cosmic radiation, now electron ion pairs are generated. These electron ion pairs, they are attracted towards the respective electrode, and while transiting from through the space, they gain energy from the electric field, they become energetic, they collide with the remnant particles, and in that process they create further ionization, that is multiplication of the ionization. Now see what is happening. I have told you that when the electron collides with the ion, it gives very small fraction of energy, remaining energy it is retaining. When the ion colliding with the neutral, it transfers all this energy. Now these particles are continuously colliding with each other. Now what is happening as the effect of that? Electrons in the low pressure environment, they become more energetic because in collisions, they transfer very small fraction of the energy and they retain the maximum energy, again gain energy from the field, again collide, and in that process, in this volume, you end up in getting a separate cloud of electron with if you define the Maxwellian average energy of that, then you have one Maxwellian from electron and other Maxwellian for ion and neutral. So when we talk of the energy of these particles, we talk of energy equivalence is always spoken in the plasma language as temperature of those particles. And if you have 1 electron volt temperature of the electron, that means high energy, it is equivalent to 11,600 degree Kelvin. But don't worry about this 11,600 as 1 eV, because the electron temperature in your tube light plasma is half eV almost. And this half eV, now you will say, with such a highly energetic electron, why the tube is not melting? Okay, because it is not melting, because even though the energy of the electrons is very high, the amount of energy that is exchanges with the walls is very, very small, because the mass is very small, momentum exchange is very, very small. So as a effect of that, now you get a low pressure non-equilibrium plasma. What is equilibrium plasma? Equilibrium plasma is the one where all species will have the same energy, same Maxwellian. Here you have two Maxwellians, one for electron and one for ions and neutral. So that is how you ended up in getting non-equilibrium plasma. Now this low pressure plasma, its uniqueness, what are the uniqueness? It's a non-equilibrium plasma basically. Because of this non-equilibrium nature, it has the capability to generate chemically reactive species at low temperature, that is due to non-equilibrium nature of the plasma state. And it also leads to high reactivity in the plasma state, because the electrons are very highly energetic state, high electron temperature, and then your ions and neutrals. And now you see, you are talking of highly energetic electrons, ions, neutrals having different temperatures. And this is a state of high internal energy, because you have presence of all charged particles with having very high energy. So this state of high internal energy, in this state, processes that are thermodynamically allowed but kinetically hindered, they proceed at very high temperature. I will give you the example. See, in the you have seen these watch cases which are coated with titanium nitride coating, golden yellow color coating. Now, this golden yellow color coating on steel, how it is given? It is given you even on cutting tools that are used in your workshop. See, your titanium tetrachloride, nitrogen and hydrogen, or titanium tetrachloride and ammonia, they are decomposed at a temperature of around 1100 degrees centigrade, where this particle, where this titanium tetrachloride undergoes decomposition to titanium plus Cl minus. Hydrogen also undergoes some decomposition, hydrogen plus, and nitrogen will undergo decomposition, nitrogen plus electrons and all these things. And then the nitrogen will react with titanium ions to form the titanium nitride. And that is how you get those golden color coatings on your watch cases, watch cases or even your tool steel components, workshop components. Now, if you do this by conventional means, that means by applying temperature in the furnace and decomposing this product, you need temperature of the order of 1100 degrees centigrade. Whereas, in the case of plasma, you can deposit excellent quality titanium nitride at 550 degrees centigrade. In fact, nowadays, all these tool steels or tools that are used in workshop for high hardness and all this high hardness, for high hardness purpose, they give titanium nitride as the coating on that. So basically, they are made by plasma CVD or sputtering process. So that is the beauty of these things, and why it has become possible, because the plasma state is a state of high internal energy where it is decomposing the product at low temperature. It is creating very active ions or titanium, nitrogen and all these things, and that has ended up in giving me the process temperature, reduction in the process temperature to 550 degrees centigrade. Now this is a very big gain in terms of your industrial production, because if you are using tool steel, which is like you are given some treatment for steel, and if you are taking temperature of 1100 to 1100 degrees centigrade, then you are basically tampering the microstructure of the steel. So if you are derived some advantages because of microstructure modification, the steel will get annealed out and you will lose those advantages. So it is always desirable that you should have lower deposition temperatures, and that is possible using this plasma. So I have just shown you one example. Another thing, now this plasma processing and another associated technologies, they are having very large number of applications in manufacturing processes. Number one is electronics industry, microelectronics components including micro electromechanical devices. It's a very critical technology for aerospace, automotive, steel, biomedical and toxic waste management. Deposition of thin films for various functional applications. See, this is a very hot field. In fact, today plasmas are having the maximum number of applications than any other tool. Actually, it's used as a manufacturing tool for most of the industries. And your semiconductor industries, they are solely relied onto this plasma processing. Because if you want to deposit solar cells or diodes or triodes, transistors, ICs and all this, you need all this plasma processing at each and every stage. So it has become a very vital component for the semiconductor industry. Then again, surface modification of components via chemical vapor deposition and plasma spray process. I do not know whether I will get the time today to discuss with you about plasma spray, but whatever is possible, I shall talk on this low pressure plasma side. Then synthetic of new exotic nanomaterials, plasma based welding and cutting, plasma assisted etching and cleaning of the surfaces, decontamination of surfaces including food and agricultural product. It has become a very hot field nowadays for processing of foods by cold plasmas. Then plasma polymerization for making corrosion resistance coating or even hard coatings. Large area deposition of coatings, good quality coatings of diamond like carbon, cubic boron nitride, super hard, nanocomposite, biocompatible coatings, carbiding and attarding of surfaces, processing of polyesters and synthetic fibers, nanoparticle generation, chemical vapor infiltration for making metal matrix composites, plasma etching, sputtering, and many more applications, including medicine, plasma medicines. That's a field which is now for all above mentioned applications. Variety of plasma sources are required to be developed, and that will provide low pressure temperature environment to the atmospheric pressure low atmospheric pressure low temperature or high temperature environment, depending on what process you want to use. Here we will be discussing about some low pressure plasma sources. Particularly I shall be discussing those things where I was involved during my tenure both at Bhabha Atomic Research Center and IIT Bombay and elsewhere also abroad. And basically some emerging trends and research opportunity will be discussed. So this we have already discussed. Now I will come to this tube. This is very simple device. You have the glass tube. Simplest thing is you have the glass tube in which you have the two electrodes, and there is a gas under the reduced pressure, and there is a applied electric field. Positive is connected to the anode, negative is connected to the cathode, and because of the background radioactivity or cosmic activity, there is ionization, electron ion pairs that are generated. They will be attracted towards the respective electrode. They gain energy from the applied field. They collide with the background gas, and plasma is generated. Again, this plasma that is generated in a simple device like tube, low pressure gas tube and two electrodes, you will see this something like this. Actual picture like this, see, you have some regions. You have some regions which are brighter, some regions which are dark, and all those kind of things. And this is coming because, see, when the electrons, they start from the cathode, they go on gaining the energy. When they become more energetic, they create ionization. Because of the ionization, again, they lose energy. Again, like they have low energy, so they cannot create ionization. They gain energy. Again, ionization happens. And whenever there is ionization, there is a recombination also. And recombination generates the light. And that is why you end up in getting the light in different regions in the discharge tube. And these dark spaces, etc., they are again named after the scientists who discovered that. I will not go through these details because that will be too much for you. But I will go through this slide. See, from the cathode, as you start towards the anode. Now, see, once the plasma is generated, you have electron, ions, excited neutrals, and these particles are going towards the respective electrode. Okay, and they are having different mobility. Electrons being the lighter particles, they are having very high mobility. Ions being very sluggish particle, heavy particles, they have a very slow velocity. And because they are very slow velocity, they move slow towards the cathode, resulting into this negative glow and negative glow discharge and if you see the potential that is applied across the tube, the potential division is something shown here. Unfortunately, the laser point is not working on this. But if you see this, this is the potential that is applied between the two electrodes, and maximum potential will be appearing across this negative glow and the cathode, and then remaining potential will be appearing across this full tube. This is the region which is the positive glow and which represents basically plasma. Negative glow is the region which is representing basically positively charged, positive space charge, which is getting accumulated towards the cathode. Now, see again this like potential and all these things, I will skip this from this discussion. But in this tube, if you take the VI characteristics of this tube, you will get this different region, like in a very, this is a current in the two electrodes, and this is the voltage applied between the two electrodes. At very low current, when the voltage is low, at current is very low. As you increase the voltage, then current also will shoot up, but very slowly. Then you get in that Townsend discharge, there is it's called a dark discharge. There is some ionization, that means the current is increasing, but you don't see the luminosity. But when you go on increasing the current, like you get the luminosity in the tube and you get the glow discharge. Then again, when you go on increasing the current density, that can be only at the cost of increase of the voltage, and so you end up in this abnormal glow region. And if you go on increasing further current density, then you will end up in an arc. Now all these things have their different applications. Abnormal glow region is the one which is used for most of the nitriding applications and processing applications, because you have very high current density, and this arc region is used for your plasma spread application. If the time permits, I will show you at least some figures on that. Okay, now simplest one, this is a very simple example. Like you have the two electrode, a plasma is generated, argon plasma. Argon is the gas which is benign gas. Now this is the cathode, this is the anode. So once the plasma is generated, the ions will get attracted onto the cathode. Ions being the heavier particles, they will exchange momentum, and as a result of that exchange of momentum, cathode material will come out of that, because instability will be generated, and this cathode material then you can deposit onto some substrate that is located in between the two electrodes. And this is a process that is very routinely being used in semiconductor industry for making electrical contact, or even for fabrication of ICs, etc., for making the electrical contact, making some metallic thin films into the IC and all these things. Okay. Now, in order to, this two electrode configuration is okay for simple metallic film deposition. Insulators, of course, cannot be deposited by this process, because in the insulator you cannot sustain that current. And to increase the current density, you are putting some magnets behind the target, your cathode, so that these flux lines are like this, and in the vicinity of the cathode, whatever plasma species are generated, the electrons, they will gyrate around these field lines, and because of this gyration, like they are confined there, they are getting energy from the field. When they become energetic, they can create more ionization. More ionization, that means more number of ions, and this more number of ions can hit the target, your cathode, and increase your deposition rate. This is industrially used process almost in all semiconductor labs and most of the industries, like working on hard cutting tools and all those kind of things. Okay. Now, the role of plasma, again, I have explained to you in the beginning itself that you have very highly energetic electrons, very low energetic ions, and these electrons, they help you in decomposition of the gaseous species very efficiently. So, because of that, you end up in getting low deposition temperature and effective ionization of your gas, etc. I will skip this discussion because that will be too much for you. I'll just show you some picture or some example. Now, this is one example I have taken, which is used by the steel industry. You know that steel as such is a very hard material. Its hardness is around 2 gigapascal. Okay, and how will you define the hardness? Hardness is defined as the resistance offered by the material for the pointed load. That means if there is some tip with sharpness, it is pushed onto the steel surface, it makes some impression. So that load divided by that area of impression, that will give you the hardness. Now this hardness for steel is around 2 gigapascal. Okay. Now you know steel has a composition of iron, silicon, very small amount of silicon, chromium. Chromium is there, iron is there, silicon is there, and there are many other metals. Now if I can diffuse some nitrogen into this steel by some means, then I can make the nitride, like iron nitride, chromium nitride, silicon nitride, and all these nitrides, they are ceramic phases. They are ceramic phases, covalently bonded materials, with high hardness. And if you can deposit or you can diffuse nitrogen into the steel, that there is a nitrided case that is formed onto the surface of the steel component, and its hardness can be reached up to almost 8 to 10 gigapascal. Almost 4 times. See, steel has a hardness of 2 gigapascal, but if you can diffuse this nitrogen into that steel matrix, it can give you hardness up to 10 to 12 gigapascal, depending, at least 8 gigapascal is minimum. Now, you will ask me, like, what is the use of this nitriding and all these things? Yes, nitriding is having a very large number of applications. I will tell you just one example is automobile industry. Automobile industry, like you have gears, now you are using these car gears, etc., like continuously, and so they undergo wear and all those kind of things. Now, if you are using some cutting tool in the workshop, then if the tool made of stainless steel is lasting for 1 week, and every doubling of the hardness of that tool will enhance its life by 10 times. That is thumb rule. There is no mathematical equation, but that is generally the observation. So imagine from 2 gigapascal to 10 gigapascal or 8 gigapascal, if I increase the hardness, how much will be the life increase of that particular tool. So now if I want to have a very less amount of wear on that component in service, I try to make it hard. Now yes, I can make it hard, but out of that hardness, there is one fracture toughness of the material comes down. Because if you materials become hard, but its fracture toughness, that is ability to absorb the shock, it becomes it gets reduced. That is because of the covalently bonded material that is formed onto the surface of the steel matrix. Now, it should not happen that in an effort to achieve the high hardness, the fracture toughness has gone down, and when I am trying to change the gear of the car, the gear sticks comes out, and then it fractures and falls off. Then it has no meaning. So you have to basically have a compromise between the two, and solution is, what is the solution then? You produce a hard wear resistant surface outside, with tough resistance core, like tough shock resistance core. And both this treatment involves diffusion of nitrogen into the surface of steel to form the layer. So this is basically the scenario. You have the steel component, you have the this is your tool component, this is a diffusion layer in which the nitrogen can be diffused, and this is the layer in which your compound layer, that is nitride phases, are formed. And again, these nitride layers, they form as a mixture of two phases: epsilon phase, that is Fe2 to 3n, and gamma phase, that is Fe4n. And it is the gamma phase that is required because the epsilon phase is hard but is brittle, and gamma phase it is having good fracture toughness. So the objective is to get that gamma phase. Now, as a see, most of the work on this plasma nitriding, people were using this gas nitriding. Again, when you want to diffuse the nitrogen, you basically need to hit the surface, and once you hit the surface, you can diffuse the carbon or nitrogen species into that to get the I will skip this discussion because time is not there. See, basically what is the process? You hit the component, there is ammonia that is coming onto in contact with the surface. Catalytically it undergoes decomposition, it creates hydrogen and nitrogen, and these nitrogen ions, etc., they interact here. They will form the precipitate, hard precipitates here. They will also form some nitride phases, and you will get the effect of the nitriding. People were using gas nitriding. Again, this is a phase diagram. I will not explain this because it will be too much time consuming. So basically, depending on the temperature of treatment and all these things, you get different phases of nitride. But you don't worry at this moment, because that itself will take one full lecture. Okay. Basically, this nitriding process, three processes were used. Gas nitriding, in which ammonia is decomposed catalytically onto the steel surface, which is hot. A molten salt bath nitriding, where cyanides cyanides mixtures, they are molten in a molten state, and components are immersed into that at high temperature. But the cyanides, they are the poisonous compounds, so that process has been environmentally banned. And then again, third process is plasma nitriding, again low pressure plasma nitriding, that is the one which is used. So basically, the gas nitriding, you have the components that are kept here into the chamber. Chamber is heated to around 500-600 degrees centigrade, and when you feed your ammonia, etc., it undergoes catalytic decomposition. All these nitrided cases are formed onto the component surface. Remaining ammonia is bubbled through the water, and it is dissolved into the water, and you get the nitrided case onto this sample surface. Now, here, by default, you get mixture of epsilon phase and gamma phase, Fe2 to 3n and Fe4n. And when there are two phases, there are two crystallographic phases. Two phases are having two different coefficient of thermal expansion. So when you service, like when you are cutting something with this nitrided component, the two phases, they will expand differentially because they have the different coefficients of thermal expansion. And that will develop the cracks, and because of this cracks generation, there may be peeling off of the nitrided case. So that is why your objective is to get single phase, and that single phase, getting single phase onto the nitride by the process of nitriding is not possible by this gas nitriding, but by plasma nitriding. Now, of course, there are very large number of these are gas nitriding unit. I have taken from the literature again. Big size component, they are being nitrided for industrial use. Again, this glow discharge nitriding or plasma nitriding, you have this on cathode, and this your chamber is anode, which is grounded. You apply the negative potential here, positive is grounded here. There is a gas that is filled, nitrogen and hydrogen, and because nitrogen and hydrogen is there, you generate the plasma containing nitrogen ions, hydrogen ions, and all these things. Hydrogen ion will remove the oxides onto the steel, and you can have very precise nitriding of the components, and we can achieve single phase nitride onto the case of this component. And this process is now industrially well adapted. This is the process, like you feed the gases, and again, you see you have a very large number of components, thousands of components, like cutting tool bits or cutting bits, etc., tools, etc. So they are mounted here. This is your cathode, and on that cathode all these things are electrically connected onto the shafts. So your cathode surface area is now this full area. You have to calculate how much is the area, and the chamber, outside chamber will be your ground. You apply voltage, you should have a very power supply which is capable of giving at least 1000 volt and very high current. Because you see large number of components are there. I will tell you one example. This our nuclear submarine people, they approached to us. They wanted to do the plasma nitrogen of a steel pipe which was 40 meters long. So they approached to us whether we can do that. Yes, in principle it is possible, but the capability of the power setup to supply current of the order of 1 to 5 milliampere per centimeter square, those kind of power supplies cannot be developed here. So because of that, we have offered them, we can do it in pieces if you can accept that. But they told this pipes or nitride component is going to go with the nuclear submarine, and we have to have a single piece. The pipes cut into various pieces. That is not acceptable by the nuclear submarine, because nuclear submarine is for defense application. So see, imagine there is a very big challenge in this whole thing. Now these gears and all these things, you have all these heavy duty gears, and then you see these are all the plasma is generated into the chamber, and this plasma that is generated here, now it has nitrogen, hydrogen ions and all these things, and these components, they are negatively biased because they are on the cathode. Cathode is at a negative potential, so it will attract nitrogen ions and give you the nitriding. See, these are again gear cutter while plasma nitriding. Then various components, automobile components, they are being nitrided. Then what is the advantage out of this nitriding? It improves the surface hardness of the components like gear, wheels, crankshafts, dies. It gives you reduced corrosion. Because see, Navy people, these submarine people, they wanted to nitride the component because of corrosion aspects. Then it improves your high temperature strength, and effectively it increases the part surface life. Okay, I will just keep this because again this is how the industrial plasma unit looks like. You have the plasma chamber and this is the power supply console. Okay, carbonitride is again, if you feed carbon and nitrogen together, you can form some carbide and nitride mixed phases. But again, they are hard phases because they are ceramics. So this process is called carbonitriding, and there is another process called carburizing. Again, industrially used process. This is a plasma based process. Again, a component is heated to 1000 degrees centigrade in a furnace. A plasma of methane is generated, and on a high temperature surface, the carbon and the ions, they diffuse into the surface, forming the precipitates into the matrix. At the same time, they form some hard carbide phases onto the surface. So it imparts high hardness, and because of the precipitate hardening, it also gives the inherent hardness to the core. Okay, so okay, this I will just skip because we have. Okay, now these are all variations. Active screen these are all like, if you go into a very big detail of plasma nitriding itself, I take 2 lectures when I offer a course in IIT Bombay. So plasma nitriding, one topic, 2 lectures are needed, so it will not be possible but to discuss everything here. But active screen plasma nitriding is the one, like you have this cathode on which you mount your samples, and on that there is a mesh, and that mesh is made as a cathode, and that one, because there is an inherently advantage of this, because there are no high voltages that are appearing on the cathode, that means onto the material. So basically, if there are narrow holes onto the component, then they give hollow cathode effect. So basically, the electron traps into that. The 2 walls have the same potential electron trap between the 2 walls. So the electrons, they undergo pendulary motion between the walls. It gains energy from this repulsion out of 2 walls. It becomes energetic. It undergoes heating. It gives heating to the component and possibly arcing and all these things. So again, if you are ending up with the arcing, then it's too much because nobody will buy your component. In fact, They have precisely done the machining, and if you are allowing arcing to take place, that process is not there. But at present, industry has accepted this active screen plasma nitride. Around the component, you put this screen, metal screen, and that screen is made as the cathode. Okay. Now, plasma nitride, I just want to show you one advantage. See, the process, gas nitriding used to be done around 600 degrees centigrade. Plasma nitriding is anywhere between 400 to 600 degrees centigrade. Gas nitriding uses ammonia and hydrogen. Plasma nitriding can be used benign gases like nitrogen. See, ammonia is dangerous gas. See, when we are in our 10th and 12th standard, it's very nice to smell that ammonia bottle because it's very much diluted. But when it exceeds 20% in the environment, it can be fatal. Like there are accidents, people can die out of that. Okay, so if there is a leak in the chamber, and then leak can invariably occur because it forms a corrosive mixture inside the chamber at 600 degrees centigrade. So it's a very dangerous process. And see, so therefore, plasma nitriding, it can be used with the benign gases like nitrogen and hydrogen. Then carburizing for precursor can be carbon dioxide and all these things. Here, we can use methane as the precursor. Then gas consumption is 400 liter per, I have taken just for the sake of comparison, 4000 liter per hour. That is the amount of gas you need in gas nitriding. Here it can be of the order of 400 liter per, 10 times lower. Then high influence of cleaning on the nitriding. We see all steel components, etc. They are basically processed at high temperature. So no matter what you do, it has always some oxide scale onto that. So even before nitriding is done, it needs a very thorough cleaning, and that cleaning is very expensive because you need to have ammonium chloride cleaning and all those sort of things. Here you don't need cleaning, you can just clean the surface by a process called sputtering. On the cathode you apply the negative voltage, positive argon ion bombardment, it will remove the oxide scale onto the material. So that is big advantage. And most important is, this ammonia use can be prevented. You can go with the benign gas like nitrogen. You know that nitrogen is not a problematic. Now, I have one slide for those of you who would like to become entrepreneur. See, these are the automobile gear manufacturing capabilities that was in the year 2007 and 2013. But the data I have taken from some literature. Japan, 2007, it manufactured 24 million gears, and in 2013 it has gone to 27 millions. Western Europe from 18 to 21 millions. North America 10 millions per year to 12 million per year. China 5 millions to 9 millions. Today it will be too much because China is now maybe manufacturing more than any other country. South Asia from 2 million to 5 million. Eastern Europe and South America from 4 million to 7 million. So on the average, if you take 28% increase in 5 years, this we are talking, now we are talking 2025. So imagine how much is the requirement that has gone up. So, and non-automotive gears are not included in this list, and they are almost numbering of the tune of almost 11 million gearboxes additionally per year. So this industry has a lot of scope, and plasma nitriding is the process now for this whole thing. Okay. What is the time? So, okay. Let me have some. So I have shown you basically the example of DC. Now there are so many applications, so many examples, but everything cannot be discussed here. I will just show you another class of plasma, that is radio frequency plasma. Now radio frequency plasma, basically they are the plasma that are generated at a low pressure of the order of 10 to minus 2 to minus 10 torr, and 1 torr is 1 millimeter of mercury for those who are not familiar with the unit of the pressure. Okay, 760 torr is 1 atmosphere, and so when you talk of 1 torr, that means you have removed the gas molecules from the chamber to a tune of 1 by 760. Okay. Now, so basically this is another class of plasma generation. How it is done? You have 2 electrodes, And in these two electrodes, rather than connecting your DC, you put a radio frequency generator, which is typical frequencies are 13.56 megahertz, 13.56 into 10 to 6 hertz. Okay, and this radio frequency power is coupled to the electrode. Here, inside the chamber, you have the gas. Radio frequency power is coupled through the matching network, which is nothing but a LC combination, LC circuit combination. So basically, you have fed the RF power into that, which is oscillating, and there is a gas under reduced pressure. So because of the cosmic activity or background radioactivity, whatever ionization is formed, the electrons, they are subjected to this radio frequency energy. They will undergo acceleration, but again they will undergo deceleration if their direction of motion is not changed. But because there are large number of collisions, so it's like when the electron goes here onto this cycle, and if its direction is changed, then again it is favorably oriented for acceleration. So in that process, it will go on gaining the energy, and once it is gone gaining, when it gains sufficient energy, it creates the ionization. Now, once this ionization is done, this ionized plasma can be used for various applications. One of the classic example is, see, your sputtering process, where you are removing the material by energetic argon bombardment and then depositing the sputtered material from the cathode. It cannot take place when if your substrate is insulating. But in the semiconductor manufacturing, like making ICs and all these things, you have to have large number of insulators that needs to be processed, like deposited, SiO2, Y2O3, and all. If you want to deposit a capacitor into while making the IC, then you want to sputter SiO2. There on anti-reflect, for giving anti-reflection coating on solar cell, you need to deposit Si3 and 4, silicon nitride. These are all insulating phases. And because they are insulating phases, they cannot be sputtered by DC process. So here in radio frequencies process, you have the radio frequency power that is coupled to the chamber here through a blocking capacitor. And what is the function of this blocking capacitor? See, your sinusoidal, like for the example, your sinusoidal wave is going from here. So during the positive cycle, electrons are attached onto this electrode. During the negative cycle, lie. So you want me to take some few minutes break? But what about the students? They are not getting tea? नहीं बस बहुत हो गया. Okay, so you enjoy your tea. I will start again. Now, see, the radio frequency waves are going from here, connected to the cathode. There is a sinusoidal voltage. When the electrode, again, through the capacitor, the radio frequency wave can very easily go, because 1 by j omega c will be reactance. So it is almost short for the radio frequency waves. Now this cathode gets that power, and it is transmitted to the spaces into the chamber. Now when the cycle is positive, the electrons will be attracted onto that, and there will be electron cloud that is sitting here. When the cycle is negative, equal number of ions should come and neutralize that charge, which is not happening, because the mobility of the electrons is high as compared to the mobility of the ions. And as a result of that, a steady state electron space charge, negative space charge, is developed onto that blocking capacitor plate side, and as the effect of that, this becomes negatively charged, because that will give rise to a steady state negative potential, and that potential will appear across this. Now when that potential appears across this, it will push the electron cloud from the plasma, and attract the ions. And these ions, they will do the sputtering, that means removal of the material, and then you can get it deposited. This is the process again which is used in the industry. All semiconductor laboratories, they must have these sputtering units. Okay, this is the one that I have developed during at my parent institute, Bhabha Atomic Research Center, for deposition of diamond-like carbon SiOx thin films for various applications, including corrosion resistance application, high hardness, and the most important application of this was development of coatings onto the infrared optics that are used by military radar application. These military people on battle tanks, etc., they are using germanium optics, which is transparent to IR because they are basically night vision devices. So now again, these battle tanks and all those things, they have to go through all hostile environment, sand particle, dust, and all those kind of things. So if you are using very highly polished germanium surface, then that germanium surface will get damaged, and your image quality will come down. So basically, they wanted infrared transparent coating, which is hard and which is again can be deposited on germanium mirrors. So this process we have developed and we have transferred it to defense people. Basically, the red one that you are seeing is the plasma. Again, by using mixture of methane and hexamethyl diacylhexane precursor, we have developed this process. We have deposited this technology for 8-inch diameter coating, and this was given to DRDO people for further application. Okay, another thing I will show you is another class of plasma, that is inductively coupled plasma. Like rather than giving RF power on the two electrode, if I have the quartz or dielectric cylinder and on the copper coil is wrapped, and then I put the RF energy into this copper coil. Now this is a RF signal, sinusoidally varying signal, varying at 13.56 into 10⁶ hertz frequency. So this RF signal, that is RF current that is going through the coil, that will generate the axial oscillating field. And this axial oscillating field that is generated along this axis, that can be sustained only when there are currents to sustain it. Now from where those currents will come? Currents will come because there is a gas inside this cylindrical volume. This gas is ionized because of the stray ionization. Electron ion pairs that are generated, electrons, they will undergo acceleration under the influence of this generated. See here, you have the copper coil that is wrapped around the quartz tubing or dielectric tube, and then this is the electric field that is generated out of the oscillating magnetic field. And because of these electric fields, the particles that are generated, electrons basically, they undergo acceleration, they gain energy, they become energetic, and they can sustain the plasma. Now, this technology is used nowadays